Yeah, what we want to talk about now is what's called power series. And it's so called because we're talking about a series, and what we're going to have is powers of x are going to make up this series. This is the most basic one. And again, they can usually start at 1. Oops. Yeah. Back to count 1 there for a minute. Yeah, so usually the end starts at 1 unless it may 1 or 0 are the most frequently starting places for those. But yeah, it's called a power series because it's just powers of x involved some way, somehow. This one, I guess you can, one way you can think of it is it's an infinite polynomial. It doesn't have an ending here, but it's powers of x. And yeah, like I said, you may start at 0 so you can get a constant involved maybe. Yeah, if we start at n equals 0, we'd start at 1, and then very well could do that. But anyway, an infinite polynomial. Now, like I said, there's good news and bad news on that. It is an infinite polynomial, and so x is a variable itself. I guess n sort of is a variable there. So we're talking about series, but it's got quite a bit more complication because, yeah, x can be any number we want it to be. Whether we want the base to be 0.1 or whatever. X can be negative. That'll add some extra stuff to it too. But the good news is on this, we are dealing with basically the same. I mean, we'll add extra stuff onto x to the n. This is just the most basic one. Some other expression for n, and we may do x minus 1 to the n. But the good news is, for the most part, we're talking about these are geometric series, is what we're talking about. If you think about it, because depending on what x is, n is in the exponent. This is an exponential function. Another way to look at it. N is in so it's geometric in that regard. And so for the most, what we'll be thinking about is where these series actually converge. The series that actually, where can we say this series converges to numbers as opposed to going to infinity? I mean, it's obvious that for some x's, this is going to get, I mean, if x is even 1, you got 1 plus 1 plus 1 plus, you got infinitely many 1. So it's not going to converge for that, or 2. But we'll look for that interval of convergence. Where, for what x's does this converge? And like I said, if you look at it, we're talking about geometric series because if I put in a 1/2 to the n, 1/3 to the n, it's going to converge for those because that's a geometric series. Now, what could we say then? Where does this converge? Well, it would converge based on what I just said. Where would you say it converges? Talk about geometric. -1 to 1, right? If x is somewhere between -1 and +1, that's where this is converging. For this one, because that's where the geometric series is converging. Now we can write that a couple of ways. I mean, we could write that as an interval, just like intervals we had before. -1, 1, meaning everything between -1 and 1, not including the endpoints. So for this reason, this is called the interval of convergence for this particular series. And like I said, you can write it both ways, it's okay. Now, another thing that'll come in, we haven't used a whole lot, probably may not have used it all, is the absolute values. We'll make use of absolute values, or absolute values will come into play here. This, both of these, well, specifically this, also is, those are the solutions to this. So that's another way, and we'll talk about the connection there between the two. But those two are the same, one and the same. If you said x is between -1 and 1, that's also another way you could write it, is the absolute value of x is less than 1. Okay? And that'll play a role in things as well. Okay. But that's what we're going to be doing. That's what power series are. Now, just some other examples. Like I said, we could throw in some other expression involving n. So this one has the square root of n plus 1 times then x to the n. And so that'll complicate things, of course, maybe change our interval of convergence, that sort of thing, or whatever. And like I said, it could start at 0, so this one would be what? This one would start at 1 as well. Then we'd have what? Square root of 2 times x to the first, no, yeah, square root of 2. Then this n equals 2, we'd have the square root of 3 times x squared. So, yeah, again, it's just an infinite polynomial that we're talking about there. Let's do it. N equals 1 to infinity. This is 5 to the n plus 1 times x to the n over n cubed. Okay. You just get all sorts of kinds. But that kind of gives you an idea of what we're looking at right there. Here's something else we can do with the power series. N equals, this is 1 to infinity also, x minus 4 to the nth over, no, just it, okay, x minus 4 to the nth. So that has some complication there, but still an infinite polynomial, just have powers of x minus 4. So as you can imagine, that'll complicate things. So in general, here's what we say a power series looks like. C sub n, x to the n, or n equals C sub n, x minus a to the nth power. Kind of have a, I guess you might say a shift there. And it doesn't have to be minus a, it could be plus a as well. But yeah, this sort of a constant kind of thing, because I guess that's why they use C sub n, but because of this, I guess because the number in front here turns out to be just constants when you plug in the n values there. So I guess that's where that C sub n stuff comes in. But anyway, that's what a power series looks like. So what would be starting off with anyway, is figuring out these intervals of convergence. So let's try one here. All right. So let's say we've got n equals 1 to infinity, -1 to the n minus 1 times x to the n over n. So I want to find the interval of convergence. Because like I said, if it's not just x to the n, we got to figure out the interval of convergence. We've got this extra stuff with x to the n or whatever it is. Well, it turns out what we can do is usually start with the ratio test. Now it's got a few more little wrinkles in it, you might say, but that's we're going to start with the ratio test. Because we know, for certain things, if it's less than 1, it's convergent, right? If we're using the ratio test. So how does the ratio test start? We look at the limit as n goes to infinity of the absolute value of the a sub n plus 1 term divided by the a sub n term. We look at that. That's the ratio test. Okay, so good news is the absolute value, so that's going to knock out right up front then, that's going to knock out the alternating sign. So pretty well get rid of anything to do with the alternating signs. And so we can focus in on just the non-positive, I guess you might say, that part of it. Okay, so without that, we could just say we've got the absolute value for the n plus 1 term be x to the n plus 1 over n plus 1. And again, we're dividing by a sub n, so that's going to ultimately result in timesing by the reciprocal of the a sub n term. So can I do that? Go ahead. Just note, yeah, a lot of these will have fractions, so we can just do the reciprocal, multiply by the reciprocal, save ourselves a step there, but is everybody good with that? Okay? All right, so yeah, we got to figure out this limit. Well, we do get some cancellation here. First of all, the x to the nth power cancels out. I guess that's all it does. Okay. Now, here's where it kind of goes different than just the ratio test for regular series, not power series. Usually what you want to do is separate out the n's and the x's. See what I'm saying? Put the n's together and the x's together. Well, in this case, there's only one x, but separate those n's and x's out. Okay? Now, we are running into infinity, so our little divide by n thing here helps us see that this is 1 over 1 plus 1 over n times x, which would just be, now it's n going to infinity, so this is 1, so that's just absolute value of x. That's what I can say that limit is. But we have accomplished something, because now I know this limit is the absolute value of x. Well, for the ratio test to work, that limit has to be what? Less than 1. So what I've found here is that the absolute value of x, for this to be convergent, that limit has to be, which is absolute value, has to be less than 1. So now I know the absolute value of x has to be less than 1. Now, So I know definitely this series converges here, okay? So I've got to start to, at least, the interval convergence. Now here's why that's not necessarily all there is to it. The other part of the ratio test, if it's greater than 1, it diverges. So if that's greater than 1, then our series diverges. So I don't need to mess with that, right? So I don't have to worry about when the absolute value is greater than 1. However, if the absolute value of x equals 1, what does the ratio test tell me? It doesn't tell me anything. The ratio test is inconclusive. So out of all this, all I can say is that definitely the absolute value of x is less than 1 and converges, but at absolute value of x equals 1, I don't know. The ratio test hasn't told me anything just yet. So what this means is I need to test when the absolute value, I have to test separately when the absolute value of x equals 1. Those two values, right? Because there's going to be two values. That means x is 1 and negative 1. I have to test those separately. Now, if we think about it, again, this means negative 1, positive 1, right? That's what that means. So really, what this amounts to, I have to test where the absolute value of x equals 1, which is x equals 1 and x equals negative 1. Well, if you look at it, those are the endpoints. So that's usually what we say. So we've got to check these endpoints separately. to find out. Because what might happen is you include one of them, not the other. You include both of them, maybe, or either one of them you include. Just how it works. Okay. So let's check those endpoints. All right. So check x equals 1. What does that give me? Well, the series then, if going back to this, if we're going to do x equals 1, we've got what? Well, 1 to the n, that's just 1. So my series is that. Anybody recognize that? What is that? Well, if it was just that, it'd be harmonic, wouldn't it? This is the alternating harmonic series. What does it do? It converges, doesn't it? And it would be, I guess the easiest way to see it would be the alternating series test. Okay, so that tells me at 1 it is convergent, so I'd have to include that in my interval, you see. Now let's test the other one. What about x equals negative 1? Well, if x equals negative 1, I'd have negative 1 to the n minus 1 times negative 1 to the n over n. What does that do? Well, here I've got the alternating signs together. What do I got? Wouldn't that be, so I've got the same base. We usually don't have same bases, but You just, if you have the same base, you can combine those by adding their exponents. Oh, yeah, we do that a lot. Which still may not help you much. You may just have to write out some terms to see what you got. But it turns out this, if you look at a few terms, n equals 1, we'd have negative 1 to the negative 1 times 1. Then the second term would be negative 1 to the third times 1/2. And then the third term would be 6 minus 1, so that would be negative 1 to the fifth times 1/3. See what's happening there? Negative 1 minus 1/2 minus 1/3. What is that?
Divergent. Oh.
It's divergent 1. That's the harmonic series, negative harmonic series.
It's not alternating.
It's not alternating, yeah. That's going to be divergent. So it's the negative harmonic series. Basically, you just factor off. If you factor off a negative 1, you got the harmonic series right here. And that definitely is divergent. So it turns out the 1 is convergent, the negative 1 isn't. And so my interval of convergence is, it's that right there, right? Okay? So that's what we're going to do here for a couple or two examples.